In this lesson, we are going to focus on wave speed and specifically what properties of the wave and the medium through which the wave is traveling through and how those affect the wave speed. So in class, you should have looked at different types of medium such as a spring, a slinky. You should have watched the video looking at different types of media and how wave speed is affected by that. Okay, so if you look specifically, think of the slinky versus the tightly wound spring. Okay, slinky, if you think, if you look at it in class, look at which one. Okay, which one traveled faster? Well, you should have seen that the wave traveled faster in the tightly wound spring compared to the slinky. Well, why is that? Well, if you think about it, mechanical waves require a medium to travel through. Okay. So, as it's traveling through the medium, what does it depend on? Well, the speed really depends on the medium itself. Okay, and that really is really the only property that determines the speed of the wave. Okay, so there's some certain properties of the medium that really affect it. The first one is the elastic property of the medium. Okay, you think of the term elastic, what that means is that anything that's elastic, it always wants to return to its initial shape. So the elastic property is how willingly that object wants to return to its initial form. So compare the spring to the slinky. The spring has that more elastic property. It wants to return to its initial shape, where the slinky, if you stretch it out, the slinky will usually stay stretched out. It's not going to want to, as much as the spring does, return to its initial form. Okay, so we relate this really to the tension force. Okay, or the spring force, whatever you're looking at. Okay, we're not always going to be dealing with a spring. You could be dealing with multiple different mediums. As you've seen in that video, you could have looked at a spring, you could have looked at a garden hose, anything like that. So the type of medium really affects, and it's that elastic property. All right. So how willingly it wants to return. And then the last one is the inertial property. You think of the term inertial. Okay. Well, what does inertia mean? Well, inertia is an object's resistance to changes in motion, right? That's the mass of a substance equals that inertia. Okay? So it's kind of the same thing here. Well, the inertial property, if we're dealing with a medium, it's really looking at the mass density of that medium. What do you mean by mass density? Well, mass density is really the mass per unit of length, which we really would call the linear density. It's kind of hard to read that there, but that's linear density. That is the mass per unit length. If you think of a tightly wound spring, that spring, given a certain length, has a lot of mass within it. The slinky is not going to have as much mass. Okay? So here you have a lower linear density, here you have a higher linear density. And that's also going to affect the speed. Okay, the lower the linear density, then that's going to change the inertial property of that medium. And kind of combining these two things, the elastic property and the inertial property, that's going to determine the speed of the wave. Okay, so elastic property, how willingly it wants to go back, and the mass per unit length, that's going to affect how it affects the speed. All right, so now wave speed in general. If you look at all the mediums through which it traveled through, so the spring, the slinky, the different medium and the media in that video, you should have noticed that once a wave is created, whether it's a wave pulse or a constant repetitive disturbance that creates that wave, you should have noticed that the wave travels through that medium at constant speed. All right. Now, we're supposed to look at and analyze, okay, how do the certain properties of the wave affect the speed? Well, does the wavelength affect the speed? Does the frequency affect the speed? Does the amplitude affect the speed? Okay, that's kind of what we were looking at here. Well, the only ones you should have seen that maybe affected the wave speed were wavelength and frequency. The amplitude did not. Now, we'll get to more what that amplitude represents, but you should have seen that these two properties are the only ones that affected wave speed. Okay? But in general, as the wave moves, or as it stays within that one medium, and that's the key here, is that as long as it stays within that medium, it's going to travel at constant speed. Saying that as long as that wave stays within, let's say, a spring, okay, As long as it stays within the same spring, it's going to maintain that constant speed. If it switches from one medium to the next, then that's going to change the speed. Okay. The next lesson will focus on waves as they encounter a boundary, and that'll look at how the type of medium will affect those types of waves, but that is for a different time. Alright, so the speed here will only change if the medium change. Otherwise it's going to remain constant, and that's kind of the important thing. Right now, right now we're focusing mainly on mechanical waves, but this also affects electromagnetic waves, which I said in the previous lesson is that those are light. That's light. And for those of you that you should have this prior knowledge already, but light travels at a single speed. Okay, it travels through vacuum at the speed of 3 times 10 to the 8th meters per second. Right? It maintains that speed, but when light enters, let's say, an actual media, right? If it travels through a vacuum, it travels at this speed. But when it enters a medium, it actually slows down. It slows down to a small amount, but it slows down nonetheless. Okay, so electromagnetic waves are also affected by the medium. That's the only property that really affects the wave. So, given that it travels at constant speed, all right, well, how can we then determine the speed of the wave? Alright, well, applying what we know, if it's moving at constant speed, there's really only one, think of the kinematic equations, one equation to solve for constant speed. Alright, do that as the x. So, looking at this, to solve for v, it's basically your change in x, or whatever your change in position over time, which is shown kind of by this equation here. Simple equation for constant speed is distance divided by time. Alright, so looking at that, well, look at distance. We're dealing with the waves. If you consider a wave that's entering a medium, consider the distance to be one wavelength. Okay, whatever that unit is, it's one unit of wavelength. Okay, so one wave will travel a distance. It'll be a distance. The distance will equal its wavelength. Alright, well, if you think about it, what's the time then? Well, that is then t will equal the time per wave. Okay, what do we call that? Well, time per wave is your period. So what you get is wavelength divided by period. That's solving basically distance over time. Okay, well, now notice here, that's simply saying lambda times 1 over t. Well, what is the inverse of the period? That's simply the frequency. So what you get here as a result is the equation that the velocity or speed of the wave is equal to frequency times wavelength. Okay, this equation here, speed equals frequency times wavelength, is known as the wave equation. So it describes, this wave equation describes all waves. That's mechanical or electromagnetic. Okay, it describes longitudinal waves, transverse waves, all those. Okay, it describes all waves. All right. This speed right here, v, this is a constant. It's constant speed. Okay, so it doesn't change. The only thing that affects that is the medium. Okay, so let's think about that. If the speed here is constant, okay, how does that then affect frequency and wavelength? Well, in order for the left side to always remain constant, okay, this does not change. Well, if you think of a wave, what if I were to increase the frequency? Well, that means if I increase the frequency, I have more waves in a given amount of time. Notice that as I increase the frequency, the wavelength of that wave decreased. Okay, the distance between a trough, let's say, and a trough is smaller than if I have a lower frequency. Okay, here the distance between crest and crest would be longer. So notice the relationship here, there's an inverse relationship, and this should make sense. In order for this side to remain constant, let's say I'm solving for wavelength, you would get that constant speed divided by frequency. Or same thing with frequency. Frequency would equal that constant speed divided by the wavelength. So there's an inverse relationship between those variables. Okay? As one increases, the other decreases in order to keep the velocity or speed constant. Okay? So that's the relationship between those two. So that means what affects wave speed? Well, really it's the medium that really determines the speed, But within that, the frequency and wavelength are what really determine the wave speed. So then that kind of leads us to what happens to the amplitude. Okay, well, the amplitude, let's think about that. An amplitude really is caused by your disturbance. So say here's your hand. Say this is a rope. Okay, if you take the rope and you lift it to this height and all of a sudden snap it back down, you're going to create a wave pulse that's going to travel through that, whatever that rope or whatever that spring is. Okay, let's say now you take same hand, but now you displace it even farther. Okay, the wave pulse is going to have a larger amplitude, still going to move in that same direction. Now what we determine is that speed, the speed of the wave is dependent on the medium, not amplitude or anything like that. So what does the amplitude determine? Well, notice as I disturbed it to a higher amplitude, the wave was bigger. Well, what does that mean really? Okay, it's going to travel at the same speed. So what does the amplitude represent? Well, it really represents the energy of the wave. Okay, so energy is represented by the amplitude, and this should hopefully make sense. If you are making a bigger pulse, you are exerting more of your energy into that. You are doing work in lifting that and snapping it back down, and you're doing more work because you're displacing it farther. More work means you're adding more energy. Okay, so you're adding more energy to that, and that's represented by the amplitude. Okay, how we solve for the amplitude is shown here in this equation. The whole derivation I'm not going to go through. All right, but the equation is 1/2. This is that linear density, angular frequency, amplitude, and wavelength. So energy is related both to, in what we're talking about, wavelength, amplitude, and also depends on the speed as well. Okay. In general, when looking at the amplitude, the relationship here is that energy is related to the square of the amplitude, meaning that if I were to double the amplitude, what does that do to the energy? Well, that gives me 4 times the amount of energy. Okay? If I triple the amplitude, that's going to give me 9 times the energy. This is an important relationship to understand, is that it's a square relationship. Okay, so energy and amplitude are related. And that's basically it for wave speed. So why don't we do an example? Okay, so here's an example. What we have is we have an electromagnetic wave. Okay, traveling through a vacuum at a speed of 3 times 10 to the 8th meters per second. Remember, these waves all travel with the speed of light. Okay, so that's 3 times 10 to the 8th meters per second. Alright, and it has a wavelength of 1.5 times 10 to the negative first meters. Now I want to know what is the period of this oscillation. Okay, so how do we do this? Well, we want to relate period. Okay, and we're dealing with the speed, and we're also given the wavelength of this wave. So what do? Well, we know, okay, we are dealing with the wave speed. So why don't we work with first the wave equation, where the speed of that wave is frequency times the wavelength. Okay, well, we are given the speed, we are given the wavelength, and we are trying to solve, really, in this case, for the period. Alright, so what do? Do we know any relationship? Well, I kind of went through this before. We should know by now that period is related to the frequency of the wave, and the relationship is the inverse. Okay, so what I can do with this equation is simply solve for the frequency, and then take the inverse of that. So frequency would equal the speed of the wave divided by lambda. Okay, and if you want, plug that right into your equation. So the period will equal 1 over v over lambda, which, solving for that, you'll get lambda over v, which, if this is the inverse, you're basically just flipping that fraction. So you get 1.5 times 10 to the negative first meters divided by 3 times 10 to the 8th meters per second. Notice you get the meters canceling out, and in the denominator you get 1 over seconds, which would carry the seconds up into the numerator. So calculating that, you get 1.5 times 10 to the negative first divided by 3 times 10 to the 8th, and you should get an answer of 5 times 10 to the negative 10th seconds. Okay. Looking at that, 10 to the negative ninth is equal to a nanosecond. So that would give you, what, about 50 nanoseconds? Okay, so that's quick. And if you think of light travels pretty fast. So that should make sense to you. Alright, so this lesson again was on wave speed. Key things to remember here is that the wave is, or the speed of the wave is really related to the medium that it's traveling through, the elastic and inertial property. Remember the wave equation, and then also that amplitude is related to the energy carried by that wave.